So we have 104 participants right now.
Mm-hmm.
Okay, let me introduce myself first. Dr. Yona, I'm Nurul Huda.
Mm-hmm.
Surayaini, they're
Mm-hmm.
colleagues from Tunggal Drama University College, Sabah branch.
Yeah.
Good afternoon, everyone, and good morning to you.
Good morning. It's very early morning out here.
Early in the morning, how's the weather over
Yes.
in UK?
Yeah, the weather is snowy,
Snowy.
cold,
Okay.
snowy, windy, snow, slippery, and I'm not a fan of it. Not a fan of it. One of them. Nope. No, I'm not a
Not
fan
a
of
fan of
snowy.
that. Yeah,
Yes.
okay. Okay, to the rest, let's welcome Dr. Yona. Orang Sabah ba ini?
Yeah.
Orang Sabah ba ini? Okay.
Orang
So,
KB,
orang KK, is it?
KB,
Orang
KB
KB.
Okay,
Tablet.
B, Kota Belud.
Mm.
Okay.
Yeah.
What? Okay, the audience today are
Mm-hmm.
actually from the diploma and degree of software engineering, not
Mm-hmm.
only from Sabah branch.
Mm-hmm.
I guess I can see they are participants from other branches also. We actually
Okay.
open it to all to go drama and music college all
Mm-hmm.
over. We have 5 branches, so we
Mm-hmm.
open it to all students.
Mm-hmm.
Okay, let's start.
Mm-hmm.
Okay, I'll give a brief introduction of you. Can so, Yona?
Are you sure?
Yeah, I'll hack you. Yeah, I
Okay.
can. Okay, so everyone, again, Dr. Yona Falinie is a postdoctoral research associate in the Department of Computer Science at Durham University, UK. She received PhD in electric and computer engineering from Brunel University, London, back in 2018.
Mm-hmm.
Prior to that, she received a master degree in electric and electronic engineering from University Malaysia Sabah. So very close to our campus. We are actually neighbor to UMS right now.
Mm.
And she also hold a bachelor in engineering degree in electrical and engineering from the same university in 2009.
Mm.
Okay, hebat orang ni ya. Okay, her research interests are in object detection, classification, emotion recognition, deep learning, machine learning, computer vision, as well as image processing. There are so much things that I guess you can share with our students.
Yeah.
And to everyone, please pay attention. I guess Dr. Yuna will have a lot of things to share with you. And do ask question at the end of the session, yeah?
Mm-hmm.
Okay, so without further ado, pass the floor or screen to you, Dr. Yuna.
Yeah. Yeah.
Okay, thank you
Yeah.
so much.
Thank you so much, Nurul Huda and Surayani, for inviting me in for this talk. So, good morning, everyone good evening, everyone in Malaysia, and good morning to me. First of all, thank you so much for inviting me to this talk. So, my name is Yona, and I am a postdoctoral research associate in Department of Computer Science, Durham University. Yeah, a little bit about myself. Yes, just like what Hilda said, I did my PhD in Brunel University, London, from 2014 and to 2018. And then before that, I did my bachelor degree, then master by research from 2005 till 2013 in University Malaysia Sabah. After my PhD, I straight away jumped into research mode as a postdoctoral in Department of Computer Science, Durham University, from 2018 up until now. So I've been living in UK for quite a long time, but I'm still a Malaysian and Sabahan myself at the bottom of my heart. Okay, let's just start this talk. So for today's talk, I'm going to give a brief introduction about what artificial intelligence and its application in computer vision. because this is the line of my research, what I'm doing full time right now. So there were a saying that an image is worth of 1,000 words. So what does that mean in computer vision context? Therefore, so the aim of this talk is to give a brief introduction of what AI and computer vision is. And then the second one is just to give an insight about what what is it doing uh, inside AI and computer vision. And then just to provide some brief context to the re-emergence of neural-based approaches within computer vision. But what I am not going to give you today is to provide an all-encompassing overview of all aspects of fast developing area of AI. I hope that you guys can stay with me and then it's okay with all of you. So, um, looking back into the questions about an image is worth of 1,000 words, what does that mean in a vision perspective? What does human interpret or percepts given a picture in the context? So, for examples, what humans see in this image. So I guess most of us will provide an answer such as a blue sky, a Ferris wheel, a tree, a big umbrella, people walking in a street, and so on. But what computers see in that the same image? In artificial intelligence version, what computers see is actually a representation of a pixel, and each of the pixel and from each of the image it provides an information about what the object is in the image. So just um, imagine that for each and every pixel in that image, it's a number. So that number provides an information for the computer to interpret what is the object in the image. So what is our job actually? The challenge is to make use the information of what computers see, which is in terms of number, which actually represents the pixels, and then try to recognize it, and then try to classify it as an object in a scene. So, what should we do to achieve that? What should we do to achieve the generalized object recognition and then image classification in this context? So why, maybe we can start to ask ourselves why we are doing this. Well, the main reason why we are doing this is we want computer to tell us what is the thing in the image. Of course, like as a human, that we know that what everything in image better that what computer would tell us. But it would be good for the computer just to help us or for to recognize what is the thing in the image that we need to know. So how do we make use of the computer or the machine that's around us right now to recognize what is the thing that we want to see in the image. So first, in artificial intelligence context, what we need to do is the object recognition. So the first module, the first and foremost main step that we should do is training, is what we call usually a training phase. So in this phase, uh, all training images, they are grouped together. Let me see. Let me search like this. This is the image that we will want to train. So we are going to group together all the training images and then get the image feature of each and every pixel in these training images. So if you see from this number over here, this could be a main representation of what is it in the image that we want to see. Then we should collect it together and then to make the image features. And then what should we do after that? And then we should do the classifier training. But before we do the classifier training, first we need to get an image feature, then we need to get the training label. So in this simple example, the training label, the over here is actually a kitchen, let's say a kitchen. In this kitchen, there are tables, there are chairs, there are lamps. So we should label all of it together to make a representation of what the kitchen is. So that's what we call a training label. For image feature, we need to uh, get all the features in terms of the numbers uh, on the image itself. So just imagine image feature is a number, uh, and then the training label is actually what the image it's all about. What is the image that we want to recognize? And then this both of image feature and training labels, it will come together uh, as a classifier, and then we train it, and we train all the image features via a classifier. And then what is the output? The output is the architecture, or maybe we can call it a model, a train, what we call a train classifier. So done. This is a training phase. Then we will go for a testing phase. So what we, in this bottom part of the picture, in a test set, again, um, we need to collect the image feature on these test images. And then we use a train classifier that we trained before on the training phase. And then it will automatically predict of what this picture is all about. So the prediction for this particular picture, it's outdoor. Bear in mind that in these test images, it's not actually being seen in the training images. But using AI, using computer vision, it will smartly recognize these test images as the outdoor scene. It never been trained in the training phase before, but because of the image feature has been learned while doing a training set. Because if you imagine, there is no much there is no distinct representation between these outdoor images and these indoor images. It's just that maybe the lighting is quite dim on the indoor images, but lighting is quite bright on the outside images. Or it could be the color of the images in the training set is maybe more or less the same on the test set. So you may agree or disagree with me, but as a general representation, whatever you train in the training images, it can get the feature representation, uh, and then it may smartly training your AI, and then it will get a good trend classifier. So a good trend classifier is needed, but to achieve a good trend classifier, what you actually need is a whole lot new, a whole lot training images so that it could generalize to a test images. So, okay, in traditional object recognition approach, um, usually before 2002, image video pixel, they are being processed via hand design feature extraction. So hand designed feature extraction is actually there are features who are not learned. That's why we call it hand design. So features such as if you're familiar with uh, SIF, SIF, SIF is actually, if I'm not mistaken, is scale invariant or feature transform. uh, HOG is histogram of oriented gradient color, which is actually, you can say RGB, red, green, blue. Maybe if you don't like RGB, maybe you can change to another color phase such as HUE or YCBCR sort of. But color in this context, a color is actually RGB, red, green, blue. So these features who are not learned. So actually it's a hand designed feature extraction. And then after we get the image feature from hand designed feature extraction, we fit each of the features into a trainable classifier. Trainable classifiers such as a support vector machine or random forest. This is a trainable classifier which is maybe often quite generic. And then we can get the object class. So this is way before AI emergence. AI it's already from 2002. It's already there, but it's just not popular yet. So this is the most popular method back then. When if you want to process your image or videos. So still traditional. So as I said before, so the image features, they are key to recent progress in recognition. So from a multitude of hand design features, they are currently in use. And then researchers back then, they are debating whether do we need to build more features or do we need to create a better classifier. So and then this is an example, a visual representation of what handcrafted features means. SFIT, it uses a key point descriptor, and then it uses a histogram in histogram of gradient. So yeah, this is a type of popular features back then. Oh yeah, don't forget there are color descriptor. When, like I said, we are playing around with a value of R, red, green, and blue. And then there's a new way of thinking of how to create a better features, or maybe on how to create a better classifier. So how about instead of just learning the classifier, we can learn more about the features too. So there is an idea uh, to learn a feature, a hierarchy, all the way from pixels to classifier. So, and then each layer, it extracts the features from the output of a previous layer. And then each of the layer, they have nearly the same structure. And then we can smartly train all the layers jointly. So for, in this example, let's say I only select a tree layer. I fit my input images, learn the features in the first layer, and then the output of the first layer will go to a second layer, and then learn the features in the second layer, and then again the output of a features in the second layer will go to the third layer, and then again learn the features of the third layer, and then after that it will go to a simple classifier. it sounds it sounds so easy, sounds so great idea. So again, so that's what we call, there is shallow versus deep architecture. So in the traditional object recognition approach, this is what we call a shallow architecture. Given an image, given a video, and then feed it into hand design feature extraction, the one that any hand design feature extraction that you like, and then goes to a trainable classifier, and then the object classes. But a new way of thinking re-emerge, which we call a deep architecture. Given an images, goes to the first layer, goes to the how many layer did you want, and then train it together, and then simple classifier, and then it gives a good object class. So that is the difference between a shallow architecture and a deep architecture. So if you in computer vision, there are usually what we call a deep learning. Deep here is essentially all the layers, they are interconnected uh, together, and then train it together, and then just to make, and then give an input of that features to a simple classifier. So that is what we call a deep architecture. So this deep learning stuff is actually draws an inspiration from biological and existing computational neural network. So what is neural network? So in biological neural network, all neurons over here, they are connected together through synapse, this small dot over here, and then uh, it will create a chemical information, and then the signal from the chemical will be transmitted to another neuron. So I'm not a biological scientist. Maybe I'll explain it wrongly. Just correct me if I'm wrong. But that's how I look at it. So, and then about this is an example of biological neuron. So if we want to translate it into a mathematical equation, or in a computer point of view, this is what we call an artificial neuron. So it's what we call a perceptron. So in artificial neural network, we mimic exactly of what biological neuron is. So all perceptron, it comes together through a linear classifier, and then information are being transmitted from there. So I guess, just correct me if I'm wrong, but the synapse, the linear classifier over here, it acts the same way as synapse over here. So it connects all input and then do all the weights and then go to one synapse and then transmit what the signal is all about. So what we're trying to do, again, what we're trying to do over here, we want to mimic what biological neuron is, and then we're trying to translate it into a computer point of view, which is an artificial neuron. So in a topology point of view, this is what it's all about. Again, we have an input images being translated as an input vector. It go to the input layer and then goes to the hidden layer, then go to the output layer, and then go, and then it will be translated into an output vector. So this is an example, is actually a one hidden layer. So if you want more layer, more hidden layer, so we will have a lot of interconnection over here, multiple hidden layer of varying size. Then again, it will go to the output layer, and then it will translate into the output vector that we want. So what is this all about? What did the neural network training do inside neural network itself? In mathematical point of view, this is what we call a weight modification. They are made in the backward direction. They are from the output layer through each of the hidden layer down to the first layer, and then goes back to the output layer again through each of the hidden layer and then down to the first layer. This back and forth connection, it is what we call a back propagation. So the key algorithmic steps, I maybe this is just a small mathematically heavy, but this is how it is. We initialize our weight to a smaller random value, and then we propagate the input forward by applying an activation function, and then we back propagate the error backwards by updating weights and biases, and then we terminate the condition when error is very small or enough iteration. We talk about error here and error there. So what we want to do is to minimize the error. So let's say if the input over here, and then we go to hidden layer over here, and then output layer over here, and then maybe the error is quite big. And then we go back to the input, and then go back to the hidden layer, and then to the output layer, and then the error, it might be decreased a bit. So you do this all over time, all over again, up until you terminate weight condition when error is very small or enough iteration. So there's a lot of things happening in the propagation details, but as of now, I guess this is just an introduction about what propagation is. So again, examples. Example of using traditional neural network in a vision application process is actually we use a real-time fire recognition. The input is actually the hue or saturation histogram, where is 10 bins of each, and then let's say for these images, it's being translated into the image image feature vector of histogram, and then also 20 element of a texture descriptor. So a traditional neural network at that time, 2011, is actually only 25 hidden neurons, well, two layer and backpropagation. And then the output is just two classes, and then fire and not fire. So this is an image example of um, if that image is a fire or just maybe not fire. So the results are 90% true positive and then 7% false positive. Mm. So this is an application of a very traditional neural network which incorporate in a real time, in a real world application such as real time fire recognition. So it is very much of an old school neural network approach at that time, using a limited number of layer and nodes per layer. That was way before 1986 and up until 2000 plus at that time. But what is the main problem actually in a traditional neural network? So the main problem back then is actually in input scalability problem. So for example, in this Albert Einstein picture, you have a 200 by 200 images. So it will give you 40K in 40K input images, which means you will process 40 times 2 connection in a fully connected layer, which translate into a 2 billion parameter. So that's a lot of parameter that we need to process each and every one of them. So what we what they did back then, they have this problem. So it's a special correlation, local, it is not global. So they suffer a poor invariance. And then also it is waste of resource. And then because at that time it is often do not, they do not have enough training samples. So again, traditional neural network, although the idea is good, but it is just falling out of favor. So because the effective training time at that time, it was limited to a small set of layer and nodes per layer due to computation time limits of training. So because we try to limit our layers, we try to limit our hidden layers at that time, because if you add more layers inside the neural network, the computation time will be higher, hence it is just not good. It's just not good for your uh for your network to train. So, and then um, handcrafted classifier at that time, such as support vector machine, it is just too good. We can't just fight that. It is outperforms standard neural network on a side-by-side comparison. It is cheap, it is fast, and then it's just good. So even though the limitation of neural network were very well known at that time, even though the idea is great. So despite the biological relationship, it's just not translate well to the direct high dimensional input images. So if you can imagine. So this Albert Einstein picture, this is actually a grayscale images. This is not even RGB. So a grayscale images is actually only have one channel, and then one channel images consists of 2 billion parameter. So imagine if you times 3 for RGB, so that's a lot of parameter. So yeah, that is what the standard of neural network problem back then. So, however, so there was another neural network approach shown in town, where in 1998, no one really talks about it, and it's just because, yeah, because it's not popular. So yeah, so what the neural network shown in town is actually a convolutional neural network. So convolutional neural network is actually a multi-layer network which has local connectivity, and then it shared weight parameter across spatial position. So the idea is just to stack multiple stages of feature extractor operating directly on the image. So, and then the higher stage compute more global and more invariant feature representation. And then it's just a final classification layer at the end. So let's just say, for this example, you want to recognize these input images of A as an A. This input images is actually 32 by 32, and you do a shared weight parameter. You do a convolutional network for each and every layer, and then you subsample it, and then after that you convolve it again, and then you subsample it again up until you reach a point where you do a fully connectivity layer, which is at the end of this layer, and then yep, you got the output using a Gaussian connection. So it sounds easy. It is another way of doing, another way of representing neural network for the images. So how did it go back then? So this is again a visualization of intermediate of feature representation from an input images to a layer C5. So let's just say again, this is an input images for number 3, because this is a hand digit character recognition. So if given an input images of a tree, so what does tree look like in the first layer? This is a number 3 look like in the first layer. And then what does number 3 look like in the second layer? So this is how it is in the second layer. Can't you see the images size is decreasing for each and every layer? But actually it is good so that your neural network can train it together. So what does it sees? What does your neural network see on in the third layer, and then again in the fourth layer, and then again in the fifth layer? So CNN is actually a neural network with specialized connectivity structure. So again, to give into details about what neural network is, convolutional neural network is just actually a feed-forward network. So it has a feature extraction, again, it has a rectified linear, and it has a local maximum, which is what we call pooling. It is supervised learning with labels, and then it trained convolutional filter by backpropagation. So this is what neural network wants, which is a backpropagation. So let's go through this layer one by one. I promise you it will be very quick. So invariant characteristic of each layer are pixel features. So it's filtered with the dictionary, convolutional, and then it is non-linearity as well. And then for each and every convolutional features, it represents a spatial information. It could be sum of all the features together, or it could be given a maximum of features together. And then if you want, you can normalize between feature response so that it is actually the number that you get, maybe it's from 0 to 1 only. So you don't get a number beyond 1, at least in this layer. So each layer in a deep CNN, it performs a different transformation. It's just a mapping from input to output, but varying in the form of convolution, pooling, subsampling, nonlinear mapping, you name it, and so on. Whereas in traditional neural network, the perceptron activation is actually the same, but we only vary the weight. So this provides a convolutional neural network with a larger parameter space to represent input to output relationship. Remember, in traditional neural network, we suffer from a 2 billion parameter. So by using CNN, we actually solve the problem because it gives us a larger parameter space to represent a complex input, and then we can map those input to the output that we want. So what is it convolutional layer? What is it convolution actually? So convolution in the first layer is immediately reduces the complexity of the input in a structure and a meaningful way. Well, actually it is based on learned weight. There is a mathematical representation of what it is, but anyway, today it's just a brief introduction. I'm not gonna uh, bring you all into the mathematical equation. So yeah, but to be fair, it's just a sharing parameter across filter uh, in order to reduce the size of a parameter set. And then what is it in convolutional layer? So the convolutional is the dependency, they are local, and then it translates invariance. And then we just only learn to have a few parameter, which means few parameters, so we can filter the weight. And then we can filter the stride, it can be more than one. It is so that we can have a faster computational, and at the same time, we can have a less memory. So in convolution layer, it produces a structure, intermediate feature maps from the input images or previous layer in the network. What is it inside the nonlinearity layer? So it provides an output mapping via a traditional activation function approach layer for each of the neuron. So we can play around with tan, we can play around with sigmoid, we can play around with rectilinear, but most commonly, why do we need to do this? Because remember what I told you about simple back propagation? So it simplifies the back propagation. At the same time, it makes our learning our neural network faster, and it avoids output of saturation issues. So what is it that we have in a pooling layer? So after we do all the convolutional layer, so we've pulled all the feature representation from the convolutional layer to form a new intermediate output layer. So when I said by pooling, either we're taking a maximum of that pooling or just some of that pooling filter response, so we can gain a robustness to the variance of location of the features and reduce the input dimensionality. So let's just say if we pull the value from here, from the hat of Albert Einstein, and we can just get a one value, which is we reduce the input dimensionality. That's what it's all about. Again, how do we do that? Again, we do localized sum or maybe maximum of a sub window. So rule of the pooling is invariance to small transformation, and then it will output a larger receptive field. Okay, what is it that we do in a normalization layer? So within or across intermediate feature maps, so before or after spectral pooling, so what we did is actually equalize the feature maps, and then after that feature maps, then we do a contrast normalization. But unlike the traditional shallow approach to object recognition using scale invariance, Fourier transform, and so on, within the CNN, we the good thing about using a convolutional neural network is the complete end-to-end processing pipeline, which is has now been learned automatically. For example, again, CNN example architecture, if we want to recognize the input layer of A, where the size is 32 by 32, so there are number of layer, type of layer, number of nodes, all down to a human designer. So there are many variants. I bet you can have your own variants of number of layer that you want, and then you can just do CNN training because it provide an efficient back propagation. So, and then CNN back become a huge success back then. It managed to recognize a handwritten text and then handwritten digits, MNES. It can recognize Arabic and Chinese as well. And then simple recognition benchmark, CIFAR 10, with this. Remember I told you before that what we did for neural network is actually to reduce the error via backpropagation. So in 2013, they managed to reduce the error to 9.3%. So the less is better. And then for traffic sign recognition, they managed to get as low as 0.56% error. But until recently, less good at more complex object recognition problem. CNN success is actually the fact that what they're trying to recognize is actually a simple images. But what if we give them a complex object recognition problem? So, people, again, the success story of CNN, they take notice of CNN's success from 2011 because three things we don't have back then on at 2000. We don't have efficient training algorithm. Back then we don't have use of GPU as of now. Now we have all the graphical processing unit, and then now we already have a large amount of training data. But some problem, they are still thought to be difficult for convolutional neural network. And then the image net challenge emerged. So we were talking about the image, but we were talking about convolutional neural network only success if we have a lot of training data. So there is a challenge, what we call the Imagenet challenge, which consists of 14 million label images with 20k classes. So this type of image are gathered from internet, and then they label it via human Amazon Mechanical Turk, and then it gives a 1.2 million training images. So at the end, they reduce it to 1.2 million training images with 1,000 classes. This is what we call ImageNet Object Recognition Challenge, which is very popular back then in 2012. So again, the results, right, year 2012, it's using a convolutional neural network, they managed to reduce the error to 16.4%. So the best non-convolutional neural network happened back then. So the error is actually 26.2%. So they prove that proof of concept. They prove that convolutional neural network managed to reduce the error up until 16 by 4%. So again, the world immediately woke up to deep learning and CNN neural network back in style, and then the success story continue. So again, this is the Imagenet Challenge 2012 winner. So this architecture is the same as convolutional neural network, but the main point is they uses a GPU implementation, would train with 2 GPU only for a week, and then bigger model. Instead of having 2 hidden layer, they have a 7 hidden layer, and then they have 650K units, and then well, there's a lot of parameter, and then they have more data, and they have access of GPU implementation, and then they have access also to a better they have access also to a better algorithm. So this is a winner back then. This become a benchmark into object classification and object recognition up until now. So, using CNN for image classification. Um, CNN, they are slow to train but fast to run at the train time. Well, uh, because it has 7 hidden layer, train on 2 GPU for a week, so it quite a long time. But just to recognize what this image is all about is actually a car. So then ImageNet detection example. So this person is being recognized as a person. So this French horn is successfully being recognized as a French horn. This is an example of an ImageNet detection. Again, if you have an occlusion in the images, so how well your CNN recognize it. So let's just say in the left images, it can manage to create 2 bounding box and then successfully detected it as a bird, which is with 86% and 70% confidence score, even though it is overlapping and it is occluded to each other. Again, detection example via CNN occlusion. A tree dog successfully detected as a cute tree dog. Again, an image detection failure, which actually makes sense. So let's just say in these left images, it's detected as a corkscrew. Corkscrew is probably a very popular device here in UK. And then, but actually the ground turret is actually a snake. But if you see it from just just a blink of an eye, it maybe you can see it something different. You don't see it as snakes. It could be where the confidence score is actually 38.1%. How about this one? This is a failure detection of ImageNet, but is this actually makes sense? This is a filing cabinet with 2.2 confidence score. This is a remote control. Well, it's actually not a remote control with confidence score with 31.8%. But actually, the ground truth is this is a refrigerator, water, and a table. So there are image detection, like the hard one, a very what we call a very hard example. So let's just say this kiwi is being considered as a tennis ball, which is there are hot dog over there. This banana is considered as a hot dog, but actually this is all strawberry and apple. This is what we call hard example. And then today, deep neural network, they are state of the art in object recognition. And then they become a state of the art for many other tasks. Do am I running out of time or should I?
You have, since we actually start late, right? Just now,
Uh-huh.
I think we
Uh-huh.
have another 10 minutes.
Oh, okay. Okay.
Okay.
It will be over in 10 minutes. Sorry, guys.
Okay.
So if you consider convolutional neural network in a real application point of view. So this is the experiment that I used before, vehicle detection with CNN. So what I did is train my convolutional neural network for about 5 hours. So if you remember, 2012, they trained the convolutional neural network for 2 weeks. So that is 2012. Now is 2021. So I managed to train it with less amount of time, but my task inference is quite high. My task inference is quite good. So I managed to detect a vehicle in a scene, but I guess sometimes my vehicle, which is actually considered as a van or maybe a bus, they are being misclassified. It is detected correctly but misclassified wrongly. So yeah, this is a problem that I should solve. I mean, we all should solve actually. So this is an example like vehicle detection. So there is an example of, oh no, how should I go to the next slide? Oh my, hang on. So let me. So this is a vehicle and pedestrian detection with, again, with convolutional neural network. So this is an example of where drone is in the image, where drone captured the images, and then we managed to detect the pedestrian in a shopping complex area. And then not only a color images, so we also leverage our detection convolutional neural network into a thermal camera. So this is just a grayscale images, but using a convolutional neural network, it managed to recognize whatever the images in a scene. However, there are key questions still remain. What is being learned actually inside CNN, and how confident should we be what is being learned there? A question: maybe can we visualize how the CNN makes decision? First layer. Well, to answer the question, yes, we can. So this is a visualization of what um what picture, what is happening inside each and every layer of CNN. The first layer, well, the second layer, the third layer, 4 and 5 layer. So what are we seeing actually over here? So if you can see in the first layer, this is just a texture representation. It, for each and every images, you can see in the first layer, it has a very general output. Every time you put an images into CNN, you will get more or less the same feature representation in the first layer. But if you go at the deeper level of your CNN, you can see that, for example, in this picture of a cute dog over here, your fourth layer is actually being translated as a feature response of a dog. And this, where else? How about these bicycles over here in the fifth layer? The feature response that you get is actually a feature response of a whale. So the deeper you get on your CNN, the better you get, the better feature response you get directly to your image input. So visualization of CNN is an important research topic. So because we attempt to understand what is being learned inside CNN. So we can see some internal representation, which may convince us that CNN are doing good job. After all, as you can see, for each and every layer, it seems like they appear to be learning the right stuff. But maybe, just maybe, we could be suffering from a confirmation bias. So we just want to make sure whether our CNN is thinking what we are thinking. So therefore, we want to look the evidence to confirm it. So what if we just distort our original images? So let's just say for this picture. So with the right question, are our CNN are always right? So can we fool our CNN? Just fooling our neural network for a little bit. To do that, what we need is actually an original image which is correctly predicted by CNN, and we distort it with a small changes of a noise, and then the new image appear. So in our point of view, as a human, we see that there is no big difference between this big van here and a big van over here, yellow van here and a yellow truck over here. But what actually CNN did, uh, what actually CNN predicted is actually wrong. So for example, what is going on over here? So this is before distortion. This is a panda, and then um we just con we just add the noise of this original panda, uh, only 0.007 distortion, and then if we use these new images and then go back to our CNN, it will predict this panda as a gibbon. So what is going on over here? Why it's not detecting our panda as a panda? So we go back to how we label our data. So there are examples that both CNN and us as a human agree on. We have such as this picture parrot, coffee pot, a black panther, fly. But there are example of CNN and us as a human we disagree on, such as this is a robin, this is cheetah, armadillo, lesser panda. So the confidence shown over here is very quite high, but we as a human disagree on CNN what is this picture it's all about. Let's just say this abstract picture. The CNN recognize this zigzag picture as a starfish, and CNN actually recognized this pattern as a baseball. So it could be because maybe baseball has this kind of color and this kind of pattern. It could be. So, but how about this? A peacock? It could be make sense. But what is going on? What is happening inside neural network that we as a human do not agree about what our CNN was saying? So I guess the main issue is the decision boundary and feature space representation. What we think CNN learn is actually not optimal. So again, the key question remains: what is being learned actually, and how confident can we be? It is how confident us as a human can we be about our CNN on what is being learned inside it. So there are core message over here. CNN, deep learning, there are lead resurgence of neural network and outperform other methods in complex image classification and many other tasks. However, clearly some limitation remain. So many researchers, me as well included, actually see CNN as a black box approach. We get the CNN, given an image, and then put it into our black box and then give the output. Yeah, that's it. So now our task is beginning to understand on how CNN work inside in images and then why. Okay, this is all great, but how do I actually get going into deep learning if you guys want to get yourself involved with deep learning? So CNN package is a free resource. CUDA, Cafe, Overfeed, TensorFlow. If you go PyTorch, we have MatConfNet. They have a resources over here. So there are good reading, further reading, good way to start. Stanford course on machine learning and convolutional neural network. It is free. All you have to do is just sign up. It is free back then. I hope that it's still free now. So there are key papers over here. And then, yeah, to the end of my talk, shallow versus deep architecture for object recognition. Neural network is very traditional, and then deep neural network is quite a new. It's not really new actually. It's varying linear type. So the key point is if you have a training algorithm efficiency and you have a GPU capability and you have a lots of training data, you can train your own deep neural network. So go forward and think deep. Thank you.
Wow. Shall we give a round of applause to Dr. Yona? Thank you so much. A very fruitful session. Thank you. Okay. There's one question here from Kambi Fong. Fong is asking, so is this what Tesla auto drive applying?
Oh,
Tesla is everywhere right now.
yes, Tesla is everywhere. So maybe I can just answer this question. This is a very general point of view. Yes, this is what Tesla are playing as of now. So the vehicle detection that I show you, so that is what Tesla wants to implement it in a real in this world. So that is what they want. But it's still a long way to go though, but we are getting there. Excited time, right?
As you mentioned, this is a starting. Okay.
Yes.
Noel Yan Lee, based on the previous recording, what does the category ignored means?
Oh, the previous. Well, ignored in that context, in that images, ignored means something that is very far from the drone camera. So let's just say if you have a drone camera and then you have an images which is very far from the drone camera, so it is being detected as an ignore. So I I just label it as an ignored over there. So it's just for me to say that okay, that one I don't really care, so I ignore. The rest I care. So yeah, that's it. It's just a matter of a class label representation actually.
Okay, I see. All right. Okay, yes. A lot of very interesting. Yeah, actually, this AI, this I guess it's a very
It
wide
is. It
area
is
to
very wide.
explore.
Mm-hmm.
Even because I'm from the multimedia side,
Mm-hmm.
we
Mm-hmm.
also have some kind of like the AI kind of thing,
Mm-hmm.
but not as I think something similar.
Yeah.
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 Okay.
So the presentation that I gave you now today is actually a small portion of an application of what AI is in a real world. I'm just doing object detection. It's just because that's my niche. That's what I like. If you guys like people with neural language processing, you can use it for NLP. You can use it for human post estimation. You can use it via money laundering, or maybe you can use it for blockchain. Who knows? If you want to do your own Bitcoin, yes, AI is there.
Correct. Correct. Wow. Okay. Basically, yeah, Dr. Yona, I learned a new words today. Convolutional neural network. What is
Yeah, I
being
googled
learned?
that just now.
Yeah, this CNN, right? Okay.
Yep.
It's a very powerful algorithm which is widely used for image
Hmm.
classification and object detection.
Yeah.
Um, from what you are doing, from what you have presented just now, I guess you are very into it. Yeah, it's very interesting. Yeah,
Yeah,
very
yeah.
interesting area to dig in. Another question. Maybe we can
Mm-hmm.
take like one or two more questions before we end
Mm-hmm.
the session.
Mm-hmm.
Jaji Chu is asking human estimations.
Yeah, it's human pose estimation. So
Process.
yep, human pose estimation is one of the key enabler in AI is actually human pose estimation. So human pose estimation is actually, if I'm not mistaken, they are trying to detect the pose of a human, your torso, your movement of your hand from your joint in your elbow. Just correct me if I'm wrong. That's what I understand. But AI, convolutional neural network can help you to achieve that. Mm.
Wow,
Okay.
yeah.
Yeah. Any question from you, Sue?
Um,
Anything that you want to?
Actually, this is also I'm not so into AI previously, but I am kind of interested already because I was involved with NLP previously.
Mm.
But when we want to study about this CNN, all of the sources that you gave just now, we can just use it. And then is there the ready, like the code that is ready for it?
Okay, let
We can
me
just use
clarify.
it.
Okay, let
Uh-huh.
me clarify when I said like the code is there, the code is there. Yes, actually, the code is there. The code is ready. All you have to do is a training resources, or maybe a training images, or it could be a GPU in your hands right now. But there is more to that than having a free. I guess there's a word, if you know, there's no free hunch in life. So the code is actually, even though it is free, but it is updating day by day. So you have to be quick and grab the idea about what the framework it's all about. Even though you can use it straight away, of course you can. There's no problem to that. But at least have a bit more understanding of what is happening inside the framework. So to achieve that level, is actually what you are doing right now. Doing software engineering, computer course, do background in mathematics. So yeah, you guys actually are getting there. That is the main fundamental aspect that you guys need to achieve first. Then you can jump straight away to the framework that I'm talking about. So of course you can use it straight away without having too many, without having uh, good fundamental. Yes, you can do it. It's just a black box, right? But actually, it would be good and it would be better if you know what is going on inside the framework. But to do that, yes, your 3 years course in software engineering, mathematical stuff. So it's important to understand what is happening inside that.
Okay. Thank you for answering all the questions.
You're welcome.
Okay, guys. Any more questions? Or else, can we have a good picture? Mind everyone, if you can turn on your camera for a while. Uh,
I'm sorry, my lighting is not so good here, but
Yeah, my lighting also is not so good here now because the light in my room is just faulty.
it's fine.
okay, those who can on the camera, or else it will look like kind of weird when there are like only two of us, three of us on the camera. Thank
Yes,
you,
please,
Noel.
guys.
Sarah. Okay. Yes, everyone, please. How to get to the second screen? So can you help me how to go to the second screen? Can you help me to take the picture? Boleh, so.
Wait, I try first.
You
I
probably
think I think the
no, we can
maximum
go to the
person that.
second screen.
Oh yeah, is it?
What? How is this?
I never have this much audience. At most, I have only 50 something. So
Anyone, can you
yeah,
help us?
yeah. Any
Your students apa? So I can take the first
your
screen. Noel, can you do that?
yeah,
Second
Noel.
screen. Do you know how to do this? I think Noel is on
What?
phone, right? You're on phone or
Phone, yeah.
computer? On phone. How to go to the second screen? Ibu tak reti pula. Okay. Let me see. Okay. Right. So Dr. Yona, smile. One, two. Okay, that's the first screen. Hold on. Go to the second screen. Oh, ramai peminat you ni hari ni. So, okay. Good to see students from other branches also. All right. Okay. I got that. Thank you so much, Dr. Yona. I hope that we
You're
can
welcome.
meet again. If not, Kak Sabah ke, who knows?
Oh yes, of course.
Yeah.
Uh,
Yeah, thank you. The rest,
wait,
take a
I
good
need to
care.
say.
Everyone, it's already week 5. You have another 2 more weeks before the exam. Yes,
Nurul,
yes,
sorry,
yes.
because I think I need to remind something. There's a link actually in our Google Calendar, but I will share it again now.
You mean this
In
one?
yeah, the evaluation
Oh,
link.
the evaluation. You got evaluation.
Yeah, yeah.
Okay.
I just want to know the
Feedback.
students
Right, students, just
opinion.
for a while, just stay for a while. Sekejap saja. Yes, you
Yeah,
just type, paste it there. Or you can
yeah.
actually later,
Uh,
we have all their emails. We can email it to them.
yeah, yeah. So it's better lah, but For those who wants the link, because I already invited you all to this Google Meet, so you all can see actually later the recording about
Oh,
this
okay,
talk
good.
lah. Okay. So
Mm.
for those who didn't get it, maybe your friends that was not invited to this, and then you can just email to me lah, email and ask for it. Okay,
Okay.
so this is my email. I mean, this is for the other student that is not from Sabah lah.
Okay.
Okay,
All right. Okay.
okay, so that is my
Dr.
email.
Yona, any social media that we can follow?
Ah. I think
Oh,
Yai knows better.
okay.
It's just
Yeah.
that my social media is not actually into academic stuff. Sorry,
All
guys.
right. Okay. 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 Understood. Understood.
Yeah.
Sorry. Okay.
Yeah.
Thank you.
Mm,
Sue, that's all right. Can we
okay.
close the
Yes.
session? All right.
Yeah.
Thank you so much,
Yes.
Thank you. Thank you for
everyone.
inviting.
Yeah. Assalamualaikum. And have a good day,
Bye.
everyone. Take care. Wear
Thank
mask.
you,
Jaga
guys.
SOP.
Thank you, Dr.
Bye.
All right.
Yona.
Thank
Bye,
you.
everyone.